Welcome you all once again. I'm Meghamala, working as Assistant Professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And coming to today's presentation, I'm here to talk about the combinational logic modules. So, what are the combinational logic modules? In this presentation, we will explain and we'll get to know more what are the different types of combinational logic modules with the examples. Okay, so before we go forward, let me explain, or else let me recollect the previous presentation what we had discussed. So in the last class we had discussed about the user defined primitives, so UDP, isn't it? So what are the user defined primitives? So under these user defined primitives we had discussed the user defined primitives are categorized into two types. So they are sequential user defined primitives and combinational user defined primitives. So under combinational user defined primitives, with the examples we had explained, we got to know what are the combinational user defined primitives by considering the examples like multiplexer, demultiplexer and so on. And coming to the sequential user defined primitives, we have discussed about the flip-flops and the latches. Okay, so by considering the sequential circuits, we had discussed what are the user-defined primitives, sequential user-defined primitives and so on. And as well, we also discussed about these syntaxes and different syntaxes pertaining to the sequential user-defined primitives and as well as the combinational user-defined primitives. Okay, and also we had discussed about the test bench syntax. So test bench syntax as well we had discussed. And coming to today's topic, the combinational logic modules. So in this combinational logic modules, we all well known about this word combination circuits, right? So what are the combinational circuits and examples under the combinational circuits? So the combinational circuits are nothing but they are the digital circuits where the data or the information is stored in the registers or the flip-flops by combining all the registers, more number of registers or the flip-flops. So here, coming to the examples of combinational logic circuits, basic examples that we can consider from the digital electronics are mux multiplexers, demultiplexers, decoders, encoders, and so on. Okay, so based on this, I mean the consideration of this, or else taking the examples of this, we will discuss about the combinational logic modules. What does it mean and what kind of implementing regarding what sort of implementations we can do easily in order to get a output. So here, coming to this combinational logic module, we know that the combinational logic forms its output as Boolean expressions, okay, Boolean functions of its input variables on an instantaneous basis. So we all know that whatever the input for every combinational or sequential circuits, whatever it is, for every circuit there is an input and as well as the output. Okay, so the input and as well as the output, they have sometimes the 1-bit input, also 1-bit output, many number of bit inputs, single output, and single input and many outputs. So all the outputs and inputs will be in form of 0, 1 or sometimes X. And also there is a possibility of getting the output in terms of Z. So what is a Z? Z is a high impedance. So usually we will see this Z, the output Z, it may occur in different combinational circuits like decoders and as well as the multiplexers as well. Okay, whenever you are giving an extra signals like control signals or the selection inputs, in such cases we will observe the output obtaining as in terms of Z. Okay, Z is nothing but the high impedance state. Okay, the saturation state or else high impedance state will be observed in the combinational logic circuits. So here, the combinational logic, it forms its output of Boolean functions. Okay, so whatever the outputs that we are getting, based on the output, we can able to write the Boolean expression. The Boolean expressions can be written based on the output that we are obtaining. And that is at any time the output, it may be y1, y2 and y3. So in the figure, we will observe there are the outputs y1, y2, y3, and it depends upon the values of a, b, c, d and t. So what is this a, b, c, d and t? A, b, c, d and t are nothing but the input. So here one thing we have to remember is the combinational circuits output we may observe in terms of y1, y2, y3 and so on based on the input that we are considering, that is a, b, c, where time is nothing but the delay. In order to calculate the delay, we are representing the delays in terms of t. Okay, time t. And the output of combinational logic circuits at any time t of any function at the time input t. That means what here you have to observe that the delays may occur with respect to the input and as well as with respect to the output, and the delays we are representing it with the t. And also in the previous classes we had discussed different types of delays. Okay, in the behavioral modeling, gate level modeling, switch level modeling as well, we had discussed different types of delays. Basically, in gate level modeling, the delays, the occurrence of delays will be seen clearly in the gate level modeling as well. So here, as we are considering the combinational circuits, we see some delays where with respect to the input and as well as with the output. So the variables in the logic circuits are binary. They may have 0 or 1. So as well, like this point is main point to remember that as we are considering the combinational circuits or whatever the sequential circuits you are considering, remember that the values will be the binary numbers 0 or 1. So the hardware implementation of the logic circuits are either positive logic with the logic 1 high, that is high voltage level say 5, and corresponds to the logic level 1, and low logic 0 corresponds to logic 0. So that means what in this like yesterday we had discussed in the user defined primitives. Coming to the combinational user defined primitives, we have seen the positive edge and as well as the negative edge. So the positive edge is nothing but the raising of the time from 0 to 1, that is low to high, and the negative edge is nothing but the high to low. Okay, the negative edge is representing with the negative edge. It seems that the level of the level of the circuit or else the level of the time delays would be from high to low, that is a negative. Whereas a positive edge, the logic values, it goes from 0 to 1. So the negative logic, a low electrical level corresponds to 1 and the high electrical level corresponds to 0. So here in negative logic, it is bit contrast. So the 1 is regarding the low electrical levels, whereas 0 regarding the high electrical level. This is in terms of negative. Okay, usually when you think logically, it is contrast to the positive. So in the positive terms, we see 1 is for high, 1 stands for high level and 0 stands for the low level. But in terms of in the negative contrast or else in the negative logic low, we represent 1 with the low and 0 with the high. And also we will consider 3 common representations of combinational circuits. So we usually whatever the circuit, whatever the digital circuit that you are considering, the common 3 representations of the combinational logics are in terms of structural, schematics, truth tables and Boolean equations. Okay. So these 3 terms are to be considered mandatorily. So if you are considering any logical circuits in terms of the in terms of combinational circuits, then always remember that we need to consider the 3 parameters. One is the structural formation, the schematics based on the gate level, okay, using different types of gate level. And the second one is the corresponding truth tables. Whatever the inputs that you are giving to such particular gate and whatever the output that you are observing, based on the input and as well as the output, the truth table is being, we have to represent the truth table in terms of inputs and as well as the outputs. And coming to the Boolean expression is a third thing that we must consider. These Boolean expressions we get from the truth table. So from the truth table output, we can easily write the Boolean expression. Boolean expression consists of the input terms and as well as the output terms with respect to the expressions. Operator, different types of operators can be used in it's a combination of the coefficients with respect to the operators that we are considering, and the formation is nothing but the equation, that is Boolean equation. And an additional representation is a binary decision diagram. This is an additional representation, that's a graphical representation of a Boolean function, and it contains information needed 10 implement. Okay, so it is just additional thing that we have to discuss. We will be discussing in the coming up classes. So the additional thing that we have to ponder is on binary decision diagram. Okay, so we will see what is it. So binary decision diagrams are used primarily with EDA software tools because they are more efficient and easier to manipulate the truth tables. So in order to manipulate the truth tables, there are some tools which are present in this era. So they are, by using that software EDA tools, we can easily manipulate the truth tables. So in that particular purpose, in order to modify or else in order to change the truth tables, we say that they are BDDs. So the BDDs are nothing but binary decision diagram. So binary decision diagrams. These diagrams are specially used in order to modify the truth tables, to manipulate the truth tables. So why? In order to get the efficient and effective manner of the output, we are using this BDDs. Next, they can also helpful in finding hazard cover. So for any circuit that you are considering, always remember that no circuit will give the clear output. Okay, some of the other errors will we may find at the time of the output. When we obtain the output, we don't obtain the 100% of output all the time. Sometimes there may be errors which are more than we expect. Okay, sometimes there may be errors which less expected very low. So all the time remember that we don't receive any 100% of results or else 100% of output effectively because of the presence of hazards and some glitches. So we will discuss what are the hazards and what are the glitches in the coming slides. So the output of a combinational circuit may make the transition even though the logic values apply to its inputs and do not imply a change. So here this point is clearly talking about the output of combinational circuits. It may make a transitional change. So it may make a transitional change by implying either at the input or else with the logic applied values. Okay. So the transitional changes may be occurred by manipulating the values either at the input with respect to the in order to get the proper output. The manipulations can be done with respect to the input terminals. Okay. Then these unwanted switching transitions are called glitches. So unwantedly, if you are manipulating any bits in the input side, then the unwanted switching transients, the switching of the bits from the input in order to get the proper output, or else in order to balance the output, the correct output, sometimes there is a chance of manipulating the inputs at the input side. So unnecessarily, if you are doing any manipulations over the at the input side, then we are calling that transitions. Such kind of switching transients are nothing but the glitches. Okay. So the glitches are the consequences of the circuit structure, the delays of an actual implementation and the application patterns that causes the glitches to occur. So unnecessarily, if you are modifying anything with respect to the input and then you are calling those such changes are nothing but the glitches. So these are the severe consequences that we may observe at the output. Sometimes the glitches can be maximum extent. To the maximum extent we may see the glitches presenting, or as a manipulation of the input side is if you are manipulating your input values to the extent, then you may see some glitches over at the output. So it's all based on the transition or as a transient response between the designer and as well based on the designer, we can say. So a circuit in which a glitch may occur under the application of appropriate input signal to have a hazard. So whatever the glitches that we are making, so that is nothing but a hazard. So this hazard, so here the hazard is nothing but the glitches it may occur under the application of appropriate input signal. So the unusual changes that you are making at the input with respect to the input, then it is nothing but a hazard. Okay, so these hazards and glitches, all these things we will be seeing when you are implementing a design, or else when you are designing a particular circuit. All these glitches and the hazards may occur. It is common when you are designing a particular circuit or else a particular module, the glitches and hazards observation are seen. So coming to the examples. So here are the examples of combinational logic modules. So under combinational logic modules, based on this multiplexers, based on the examples, we will come to know how the glitches or the hazards can be overcome. So here coming to the multiplexer, as we all know, this is one of the combinational circuits where this multiplexer, it has many inputs and a single outputs with respect to the selection lines. Okay, in the previous classes, we have discussed very clearly with the help of the syntaxes, text benches and everything. So coming to the multiplexer, the circuits are used to steer. The circuits are used to steer data through functional units of computers and other digital systems. So these are, we can say that these are the prominent combinational circuits. In order to design a particular computer or the digital circuits, these multiplexers play a vital role. That means what? In order to design a complex circuits, the multiplexers are much used. Okay, so in order to steer the data, in order to pass on the data between the modules, different modules from the input or the output, or else in order to obtain a proper output, basically the designing of the complex designing of the modules, we will see this multiplexer, the usage of multiplexer, all the implementation of, or else the designing of the multiplexer, the basic common combinational circuit multiplexers are used. So, for example, a multiplexer can be, it just used to steer the content of the particular storage register to the inputs of an ALU and to steer the output to the ALU or to the same or the different register. So here one thing you have to remember here in this, the main important point to ponder on this multiplexer is, whenever you are storing some information, or else whenever you wanted to give some information to the output, or else to the under block, if you want to pass on some information, this will be done with respect to the multiplexer. That means what? It just steers out the content of particular storage register to the inputs of ALU. So if for suppose this is an ALU and here are some registers, R2 register, R1 register. So what it does, the multiplexer always, it helps this register to give on the information to the ALU, okay, in order to do the logical, in order to perform some logical operations and in order to get the output. This multiplexer, it drives off the input using the register R1, and finally whatever the output that we are observing, that will be stored using this multiplexer. The information will be stored in the register R2. It steers out the information to the output of the ALU to different registers or else onto the same register itself. If again this register, it want to pass out the information to some other register R3, the same mechanism will goes on. Okay, so for example, a gate level schematics of 2-channel multiplexer is shown in the figure. So by considering the following figure, it is a 2-channel multiplexer. We will come to know what sort of information that it has and what sort of output that we get. So coming to here, this is a circuit. Okay, this multiplexer is based on the gates. It has been constructed with the helps of the gate. So here we had 2 AND gates, 3 AND gates totally, and we had a buffer or NOT gate. So two inputs A and B. So for each for the multiplexer 2x1, we have inputs A and B, and we have the output Y with the selection lines, isn't it? Okay, so this is 2x1. That means what? N inputs, 2 power n inputs, n output. So when selection data is 0, what happens? The data at the input passes through the circuit. with some propagation delay y out. So when the selection line is 0, what happens? The output will be observed with some delay. Okay, with some delay. This is what this says. Likewise, if set is equals to 1, that is if selection line is equals to 1. If selection line is equals to 1, then the data at the output B goes to Y. So here when selection line is 0, the input it initiates. This gate will initiate the mechanism and we will observing the output at Y out with respect to selection line 0. When selection line is 1, this gate will initiate the mechanism and at the output, Y output, we will get the output with respect to selection line 1, that is B. So the Boolean expression describing the function for this particular is selection line A plus selection line B. Why? Because here we are using two AND gates, right? And with the NOT gate. So selection line A plus selection line B. So here for every, I told you when you are considering some logical modules, combination logical modules, always remember that we have to consider three things. One is structure, truth tables and Boolean equations. So we got a structure, first one, and truth table, second one, and here it is a Boolean expression. Okay, so whenever you're considering a combinational circuit, we have to consider three things. One is the structural form, the second one is a truth table, and third one is a Boolean expressions. These are related to one to other. So coming to the truth tables, the value of the Boolean function can be assigned to the input lines and decoded by the selection lines. So we all know the mechanism of multiplexer. With respect to the selection lines, the output is being decided, okay, with respect to the selection lines and as well as the input lines. So the assign of the input lines and decoded by the selection lines. The implementation, this is nothing but the this decoder, this multiplexer is 16 by 1 max multiplexer. So this is 16 by 1 multiplexer. So for this 16 by 1 multiplexer, 16 bits are the input bits. These are the input bits. These are the selection lines. And this is the output. Okay. So we implement, the implementation must be inefficient because the must fully decode the truth table of all the input bits. Why it is insufficient? The implementation might be insufficient. The statement is telling that the implementation must be insufficient. Why? Because we had considered the combination as 16 by 1 max, isn't it? So here the different, we feel some inefficient because of consideration of the huge multiplexer, that is 16 by 1 multiplexer. So here we have 16 inputs. We have 4 selection lines and we have 1 output. So here are the 16 inputs. So you say here Y is the output, S0, S1, S2, S3. Okay, these are the selection lines. Based on the selection lines, the output is being determined. So coming to the demultiplexer. So here, before we go into the demultiplexer, always remember that in this presentation, we are talking about only the combinational logic module with respect to the examples. Okay, this is what our presentations of today. So the combinational logic modules, with the examples, we are considering mux, demux, encoder, decoder, and under encoder, priority encoder. Okay, and that's it. We may consider adder, subtractor and all. In under adder, full adder, half adder. Under subtractor, half subtractor and as well as a full subtractor. So these are the different combinational logic modules that we can observe with respect to the structure, truth table and the Boolean expression. Okay. So coming to the demultiplexer. So demultiplexer is nothing but the opposite to the multiplexer. Multiplexer is many to one, right? So demultiplexer is one to many. Okay. So it is quite contrast or else opposite to the multiplexer. So what is this demultiplexer is? The demultiplexer, it implements a reverse function of a multiplexer. So it just opposite of the multiplexer. That is, it has a single input data path and multiple output data paths. Okay, it has single input data path and multiple output data paths, and the input m bit address determines which of the inputs is connected to the input. So here we see this is the input, data in, we have data out. From data out is many, right? That is 0 to n minus 1. And also we have the address bit, the output channel selected by demultiplexer determined by the output data from 1 to n minus 1, and the address, we have the address bits from n minus 1 to 0. That is, the index of the address is being stored here in the address. The index of that particular data has been stored here. Okay, so we are representing the address bits as k. That is k, k minus 1, k minus 2, like that. Okay, so this is quite opposite of the multiplexer. And coming to the decoder, what is this decoder is? Decoder is nothing but it is a binary decoder. It interprets an input pattern of bits forms to a unique output word in which only one bit is asserted. So here we have 2 by 1 marks, right? It's 3 to 8 decoder. So n input, 2 power n output. That is 3 input, 2 power 3. 2 power 3 output. So this is a 3 to 8 decoder. So likewise, we have different types of decoders that we can discuss. So here in this decoder, a binary decoder, it interprets the input patterns of the bits in order to form a unique output word. In order to form a word, we all know what is word, what is bit, what is byte. Okay, 1 byte is equals to 8 bits, right? 1 word is equals to 16 bits, isn't it? So in order to obtain, or else in order to form a unique word, the decoder, it just interprets the input pattern of the bits with respect to the 1 bit asserted. So the decoders are commonly used to extract the opcode form from the instruction in a digital computer. Row and column address decoders are used to locate a word in memory from its address. So it will just locate a word from the memory. So if for suppose my memory is 215 gigabytes. So from these 250 gigabytes, what my decoder will do, it just decodes a word. Here my word is nothing but 16 bits of word. It just decodes from a memory. Okay, from the memory which is present in some address bits. In kth address bits, I am having my 16 bits of word, where this decoder, it just extract the opcode which is from the digital computer in the presence of rows and as well as the columns. So as I said you, in order to implement this in the logical module, always we have to consider 3 things. One is structure, truth table, and as well as followed with the Boolean expressions, right? So here when it comes to the structure, this is a decoder with inputs and as well as the output buses. Okay, you all know what is meant by a bus. Okay, you all I hope you know what is a wire and what is a bus, and what's the difference between a wire and a bus. Okay, so what is a wire? Wire is nothing but it is a single, it's a device where it connects 2 modules. Okay, so for example, it's a battery. You have consider a battery, and can consider a small what do we say, a resistor kind of, or else you consider a resistor and a capacitor, and you just wanted to, if you want to connect these two, simply we use a wire, right? But in some cases, mainly if you open a motherboard, you will see a belt kind of thing. That is nothing but a bus. What is a bus? Bus is nothing but the connections of all the collection of a wire. So this is a bus. Bus is nothing but the collection of a wire. So from the transmitter to the receiver, if you have wires of more than 100, it's very difficult for us to connect each and everything using a single wire, right? What happens? It looks clumsy, and some other disadvantages is there may be a chance of breaking also as well. Disconnection might be seen. So in order to avoid those, we use a bus. Bus is nothing but it consists of a group of wires connected to a bunch of wires framed in a particular path, and that is nothing but it is just a connector which connects the devices. So here in this example, decoder with inputs and output buses. So here we have the decoder of data input and we have the data output. In terms of buses, many number of 3 power, for example 3 to a decoder we are considering, 3 inputs 8 outputs, right? Sometimes what happens is, instead of considering 3 inputs, we may consider more inputs. Okay, more inputs, that is n into 2 power n is nothing but the decoder. So n number of inputs you are considering, you have to obtain 2 power n number of outputs. So in such cases, instead of using wires, we use the buses. And the second figure is talking about the decoder with an expanded output bus. So this is a single bus, this is an expanded one. As I said you, a bus consists of number of wires which are arranged in a sequence, which are arranged properly, right? So here my output is n. Here individual wires have been sorted out, that is from 0 to n minus 1. That means what, here the bus has been expanded to a single wires from 0 to n minus 1. And here in my data input as n input, data in with m inputs, and data out as categorized as 0 to n minus 1. Okay, now you got to know what is a bus and the difference between the bus and a wire. So the decoder, it has m inputs and n outputs. Okay, m inputs and n outputs in terms of bus. A decoder in terms of bus, but with n is equals to 2 power n minus 1, 2 power n, there are many different possible mappings between input word and the output word. So if my output is n is equals to 2 power m, so in this case there may be a chance of mapping more than different possibilities of mapping between the input and as well as the output word is being seen. Okay, so an encoder can build from the combinational logic circuits, obviously, which forms the input output mapping. Okay, so the input output mapping can be easily done with the by considering the decoders. Okay, so it can build a basic combinational logic circuits where it can map the input and as well as the output. So sequential encoders and decoders are widely used in where communication and video transmission circuits. So basically these combinational circuits like say encoders and decoders, these are widely used in communication and as well as the video transmission circuits. Okay, now it's important, you have to remember this point. Then the input output patterns of 8 client decoder. 8 client decoder means 8 to 2 power 8, 8 into 16, right? So 8 by 16 decoder, the example that we will consider in this particular slide, the arrangements of bits in the output word, it identifies the clients will be served. So here we will see the arrangements of bits, how the bits are arranged. If it is 8 input, sometimes 4 bits have been arranged, 4 inputs one time and 4 inputs with the other time. That means what, n1, n2, n3, n4 and m1, m2, m3, m4. 8 to 16 decoder means. So here the 16 outputs. So the arrangements of bits in the output word identifies the clients will be served. Next, the decoder does not resolve contention between multiple clients as it assumes that only one client at a time will request service. So here this decoder, it cannot communicate or else it cannot give the suggestions or the information to multiple clients at a time. But it can give one client at a time will request the client. So one time, one client can be, it just communicate or else it just send a request or accept the acknowledge from it. But not the multiple, between the multiple clients. One client, one request would be sent and acknowledge will be sent to the source, but not to the many clients. So a binary decoder, it generates all the minterms of its input. So all these minterms, minimum terms and maximum terms, max terms and min terms, they are present in the SOP and POS forms. We will be writing the Boolean expressions in terms of sum of products or products of sum. Sum of products or product of sum is nothing but it is a combination of the and or gates. Okay, and or gates where the expressions can be coming out with respect to the truth table that you are considering a particular device. So any kind of device, any kind of logical circuit that you are considering, you can be able to write the truth table followed with the sum of products and product of sum with respect to the binary expression. So here all the output lines are available to form as many functions as inputs are as needed by the application. So the output lines are available in order to form as many in order to form many functions of the same input are needed by an application. So here output lines are already available, and in order to in order to write many functions, the output and the input in order to write some function, we can write this function with respect to the input. Same inputs are needed by the applications in order to find some Boolean expressions. So here the binary decoders, it can be used for small implementations with multiple outputs. Okay, so here the decoder can be used for small implementations for the multiple outputs, but the number of outputs are peculiar. They use in applications with the number of inputs. So here the important thing you have to remember is we can obtain the output, more number of output. That means considered if you are considering some input, you can obtain more number of outputs, okay, using this decoder. As I said you, a perfect example is 8 to 16 decoder or is 3 to 8 decoder. So when you consider this 3 to 8 decoder, you see only 3 inputs, but the combinations of outputs can be mapped to 8, isn't it? So 8 to 16 means we have only 8 inputs, but the combinations which are mapped is to obtain is with respect to the 16 output. So here this is nothing but a 8-bit word. So this is an 8-bit 8 to 16 decoder, whereas here the input word is from 0 to 7. And my output word, if you observe here, my 16-bit output word is obtaining with respect to the input word. The combination is 0, 0, 0, 0, 1, 2, 3 like that. So if you see my 7th word, the input word with respect to the 7th input word, the output word that I am getting is 0, 0, 0, 0, 0, 0, 0, 1. Okay, so we will see here in this particular figure. This figure is talking about a 4 to 16 decoder, where here 3 to 8 decoder we have 4 to 16 decoder. 4 to 16 decoder. So here in this we have 4 inputs, 16 output. This 16 output are again categorized into 2 outputs. How? Divided by 16 is divided, 8 input to one and 8 input to other. Okay, so a decoder can be used to implement multiple Boolean functions of the same input. So this point it is talking about a decoder can use to implement multiple Boolean functions from the same input. That means what? From these 4 inputs, we are obtaining the 16 output, and this 16 output we are clubbed into 2 parts. We are divided this 16 to 2 parts, that is 8 in one and 8 in other. So we can map at any cost, but with the combinations with respect to the input. So the truth table here is this is a truth table followed with the diagram, where here in this truth table the majority function, see here we have F1 and F2, right? So F1 and F2, it combines the output with respect to the input. So my output is F1 and F2, and I am considering here as 4 to 16 decoder. So my 4 inputs are S0, S1, S2 and S3, and my output are 0. So when my 4 inputs are 0, 0, 0, 0, my output is observed as 0, 0. That is F1 and F2 both are 0. So here I can connect 0, 0, 0. If it is, I can connect 0, 0 to 15, right? So 0 to 8 and 9 to 15 connected to one AND gate, and 0 to 8 is connected to other AND gate. So here if my combinations are 0, 0, 0, 1, and then my output is connected to F2. So if it is 0, 0, 1, 0, then connected to both. So 0, 0, 1, 1. So as per this combinations, I am connecting to, if my combination is 1, 0, 0, 0, 1. If my combination is 0, 0, 0, 1, 0, 0, 0, 1, then I am connecting this 1 to here, F2. So I am connecting F2 to, so 1, 2, 3, 4, 5. And for F1, 1, 2, 3, 4, 5. Okay. So this is how I am managing, or else I am mapping. I am mapping with respect to the input. The possible outcomes are coming with respect to the input. So this is all about the combinational logic modules. So we had discussed in depth about what are the combinational circuits, and how they are implemented using different conditions. That means whatever the circuits, the combinational logical modules that you are considering, we have to remember that always the circuit that we had considered, it has to go through the three conditions. One is a structural form we have to show, and the next one is the truth table. We have to make a truth table, and based on the truth table, the Boolean expressions can be implemented using this all the combinational logic modules. So this is for today's presentation, and I hope you all understand. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.